today we're going to go over power series. So we're going to start with an infinite series. An infinite series is an expression in the form a1 plus a2 plus a3 and then infinite repeated infinitely as noted by this sigma notation. So what this means is we start with n equals 0 and then keep adding x to the n power, so x to the 0 power, x to the 1 power, x to the 2 power, until, or infinitely, as noted here by the infinity sign. If this was, for example, 5, then we would keep going until we get to 5. So the numbers bolded here, a1, a2, a3, are called the terms of the series, and a of n is the nth term. So a sub 1 is the first term, a sub 2 is the second term, and so on. A geometric series has a common ratio. So for example, 1, 2, 4, 8, or 1, 1/2, 1/4. And the series converges if a1 over a1 minus r, the geometric series converges to the sum a1 over 1 minus r if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. So the interval -1 is less than r is less than 1 is called the interval of convergence. Let's go over an example. We need to find r of this infinite series right here. So r would be 2/3 because each term is multiplied by 2/3 times the previous term, or each term is 2/3 times the previous term. So it asks whether this series converges or diverges. So this series converges because the absolute value of r is less than 1. So 2/3 is less than 1, so it converges. So it asks if the series converges, which it does, calculate its sum using a1 over 1 minus r. So a1 here is 1, since that's our first term, and then we'd have 1 over 1 minus 2/3, which is r. And then that equals 1 over 1/3, and then that just equals 3, right? Yeah. Okay, so the next question is, if the series converges, which we found out that it does, find the sum of the first 5 terms for the series at r to approximate what value the series converges to. So what this is basically asking is for us to add up the sum of all these terms and for the first 5 terms. So we have 1 plus 2/3 plus 2/3 squared plus 2/3 cubed plus 2/3 to the 4th. And that's the first 5 terms. And then if you plug that into your calculator, you'll get 2.604. So that is the sum of the first 5 terms. And then if the series converges, compare your last 2 answers, and then what do you notice? So we notice that the sum of the first 5 terms is a bit less than the actual sum, which is 3. And so we're going to put that. The sum of the first 5 terms is less true sum. Alright, so next question. Find r of this infinite series. So we're going to use the same process as we did before, and then r would be 5 over 3 because that is the common ratio that it's being multiplied by every single time. So does the series converge or diverge? Since the absolute value of 5 over 3 is greater than 1, then it would diverge. 5 over 3 is greater than 1, and then it diverges. And then if the series converges, which it doesn't, so we don't need to answer that. And same thing here. Alright, so for this next part, we're going to show how the power series works and how it approximates what the true function is, in this case, 1 over 1 minus x. So we're going to keep adding terms to a power series until we get a very close approximation to the actual function. So we're going to start off with graphing our original function, which is 1 over 1 minus x. So 1 over 1 minus x. And then this is what it looks like. We just need this part right here. So I'm going to sketch that. Look something like that. So then in this next part, we're going to sketch that same function. And then we're going to graph f of x equals 1. So f of x equals 1 is just a line at y equals 1. Oh, actually, let's use highlighter in this case. So that's f of x equals 1. So this is a very bad approximation of f of x, since anywhere you go, it's going to immediately diverge and get further away from what the actual sum is. So now if we add another term to f2 of x, we will get, so 2x, 1, 6. So then the approximation is starting to get a little bit closer, as you can see here, to the actual function. So let's do this one highlighter. And then we can keep adding terms until we get a very close approximation to what the original function is. So as we can see, as we keep adding terms, the approximation gets closer and closer to the actual function. So in this case, the function would look something like this. Still kind of far, but we get closer every time we add a term. So when we get to the sixth term of the polynomial, oh, actually that's wrong. So when we get to the sixth term, we can see that from -1 to 1, we have a very close approximation, but other than that, it starts to deviate from the actual sum. So, yeah. This is a series of functions. So the series in the function of f2 of x, that represents a Taylor series, a base Taylor series. So what a base Taylor series is a power series that's designed to approximate a certain function, in this case, 1 over 1 minus x. So we can now say that the function 1 over 1 minus x can be represented by this series right here, 1 plus x squared, and so on. So let's try some other functions. So this function, so let's see some other functions. So 1 over 1 plus x can be rewritten as 1 over 1 minus negative x, because we know that negative times a negative equals a positive. So the rewritten function matches the form of base, which is 1 over 1 minus x, x being negative x in this case. So to generate this power series, we must replace every x with negative x. So the power series for 1 over 1 plus x would be 1 plus negative x squared plus negative x cubed, and so on. Simplify. So to simplify this, we would just do 1 minus x, and then x, or negative x squared is just x, because negative x times negative x is x. So that would be x squared plus, and then since it's an odd power, it's negative x cubed, and so on. So then this next function can be rewritten as 1 over 1 minus negative x squared. So we want to keep it in that same form of 1 over 1 minus x. So to generate this power series, we replace every x with negative x squared, and then we would do the same process. So it would be 1 plus negative x squared plus negative x squared plus negative x squared cubed, and then we'd simplify this down to 1 minus x squared plus x to the 4th minus x to the 6th. And that's so in this next function, x over 1 plus x can be written as x times 1 over 1 minus negative x. And that still matches that same form. And to generate this, we just replace every x with negative x. So in this case, we just replace every x with negative x. And what we do with this x on top is we pull it out front and then put our power series here, since we can just distribute that x to every single term. So then we have, so then in this case, what we do, we pull out x to the front, and then we have 1 over 1 plus x, and then we already know how to do this this function. So we'd have in this case, x times 1 plus negative x plus negative x squared plus negative x cubed, and then simplify that down to 1 minus x plus x squared minus x cubed, and so on. And then we need to distribute this x, so that's x minus x squared plus x cubed minus x to the 4th, and so on. So this next function is the same thing as saying 3 times 1 over 1 minus x, and then that's also in the same form as base, and to generate this power series we need to pull out a 3. So then we do similar to what we did here with the x. We pull out the 3 to the front, and then that's 1 over 1 minus x, and then this is just the base power series, so this would be 3 times 1 plus x squared plus x cubed, so on. And then we distribute 3, so that's 3 plus 3x plus 3x squared plus 3x cubed, and so on. So the next function can be rewritten as 5 times 1 over 1 minus negative x squared, which again, so we need to find the interval of convergence for the last example, which is negative 1 is less than negative 2x, which is less than 1. And then we just solve it algebraically. So we divide each side by negative 2, so divide by negative 2, negative 2. And then we have to remember that when we divide by a negative in an inequality, then we have to flip the signs. So 1/2 is greater than x, which is greater than negative 1/2. So now we have to use the calculator to confirm our answer. And then, wait, so what do we plug in here? Okay, so for our next step, we're going to go to the calculator to confirm that the interval of convergence is in fact correct. So in blue is the original function, and in red is our Taylor approximation. And then as you can see from negative 1/2 to 1/2, the function is very close to the approximation. But if we zoom out, we'll see that once we deviate from negative 1/2 to 1/2, the function starts getting very different from the Taylor polynomial. So this next page is there. So the next part is to find the error between the Taylor polynomial and the actual function. So the Taylor polynomial for 1 over 1 minus x is just the base one we've always been using, so 1 plus x squared plus x cubed and so on. And we want to find the exact value of the function at x equals 0.5. So to do so, we just plug in 0.5 to the original function, which is 1 over 1 minus x, and then we get 2. So next we need to figure out the approximation for the function when x equals 0.5. So we use our Taylor series. So we have 1 plus 0.5 plus 0.5 squared and so on. And then if we use the first 5 terms, we get 1.9375. And then to find the error, we need to take the difference between the two, the approximation and the actual function, which is 1.9375 minus 2, and we get 0.0625. So next let's go over some practice problems, and we're going to use the same process for finding the interval of convergence for each one. So write out the first 4 non-zero terms, which is 1 plus x cubed squared plus x cubed cubed, which simplifies down to this. So then we would take our common ratio, which is x cubed, and then use that for our interval of convergence, and then we'd simplify algebraically. So to simplify this, we just take the third root of x, and then since this is 1, it stays 1. So our interval of convergence would be negative 1 to 1. So we need to find the first 4 non-zero terms for the power series of this function. So we pull out the 2, and then we replace every x with, in this case, negative x to the 4th, since we want to turn this into a negative. So we have 1 plus negative x to the 4th plus negative x to the 4th squared negative x to the 4th cubed, and so on. And then that simplifies to 2 minus 4x squared 16x to the 4th minus 64x to the 6th. So then, in this case, our common ratio would be negative x to the 4th. So we have negative 1 x to the 4th. So since this is all just taking roots, it would just still be the same, negative 1 to x to 1. Okay, so for the next one, again, we just replace every x with 4x. So 1 minus 4x, 1 plus 4x, I mean. 4x squared plus 4x cubed. That applies to so to find the interval of convergence, we just take negative 1 is less than 4x is less than 1, and then use algebra. So then that would be our interval of convergence for this power series. And then just, I guess, fast forward through this part since it's just repeating the same thing. for the next one, this would just be 1. We'd replace every x with negative x over 2, because this is a plus, so we need to change it to minus. And then we put that in for our interval of convergence, and we use algebra to get 2 is greater than x is greater than negative 2, so from negative 2 to 2. And then here we just pull out the 64, and then our terms will just be x, since it's just a regular base series multiplied by 64. So our interval of convergence would be negative 1 to 1. So now let's switch over to JGrasp and see how we can write our Java program and see how it compares to the power series representation of 1 over 1 minus x and 1 over 1 minus x itself.
Hi! Today I will be showing you this program designed to calculate the Maclaurin series of the base function in Java. So first I'm just going to show it in progress, and then I'm going to get into the actual code. So the first thing it asks us to do is enter a value for the series 1 divided by 1 minus x, which you should recognize as base. And we're going to put in the number 3. And you can see it gives us the full Maclaurin series and the error value. And if you were to take a look at the error value, if you were to plug in 3 into the original base equation, 1 divided by 1 minus x, or well 3 for our example, you will see that the answer is negative 1/2, and the difference between the Maclaurin series and the error is 1/2. Now we're going to try this on a slight variation of the Maclaurin series, the base series, 1 divided by 1 plus x, which you'll recognize to simply be base, where negative x is submitted for x. And we're going to try 3 again. Now here, the program has actually spit out each term of the Maclaurin series. That's just for show, but you'll see that it calculates the Maclaurin series as 61 and the error as 60.75. And if we were to plug in 3 to this version of base, so 1 over 1 plus 3, you'll see it's 1 over 4th, and the difference between the final series and the error is, of course, 1/4. So that's the program at work. So let's actually see how it runs under the hood. So the first thing it does is, of course, it scans for user input for our numbers and tells us what version of base we're going to be running, which is, of course, the original. It then, using the next double function, it stores the number we submit in the variable e, and it creates the variable result and setting it at 0 initially. Next, it runs a for loop that runs from 0 to, it ends at 5, but it ends at 5, but the last number it runs with is 4, obviously. And basically, it has the new variable r, which is equal to the power of e, which is our x value, to the power of I, and then it adds that to the results. And if you know about the value of base in Maclaurin series, that's 1 plus x2 plus x3 dot dot dot, which ending at x4, since this loop ends at 4. It starts off with 1, and since I begins at 0, whatever we submit in will be to the power of 0, thus 1, and then each of those will be to the power of 1, then 2, then 3, then 4. So result will thus store the final Maclaurin series. It then prints that, and of course we then print the error, which is equal to the actual value of 1 over 1 minus r, the number we submitted, minus the result to give us the error, which is why we got an exact error. Next, the program runs through the variation of double, again storing our value, the thing we submit at e, setting results back to 0, and it has another for loop running from 0 to 5, last run being on 4, where it has the variable r being the having the number we submit as a negative to the power of I. Now, of course, this is negative because the variation we're going for, 1 over 1 plus x, is simply base, where x is replaced with a negative version of itself. It adds all the results together, and then and we have it printing out here, which is why it showed each term, But then it prints this Maclaurin series and, of course, the error. If we were to run this again and put in 3, it wouldn't put in the terms this time. Waiting for it to run. Okay, sorry, that was a bit strange. So 3, see, we get our original number back, and of course if we put in 3 again, you'll see it didn't put in the terms and just gave us our series. So that's how the program basically works. So now we're going to be moving on to an example. Now specifically, it's going to be the example 5 over 1 plus 2x, and I'm going to be moving over to a document, a Word document, in order to show how this works with this variation 5 over 1 plus 2x. So I'm now in a Word document, so I can run through the variation of base 5 over 1 plus 2x by hand before we run back into Java and modify the program to run the function. Now, the example that we'll be working with is 5 over 1 plus 2x, obviously. And before we continue, we're going to actually want to convert this into a more recognizable version of base, and that's going to be 5 over 1 divided by 1 minus negative 2x. And you should see that that's simply just base, where negative 2x is replaced with x, and the whole thing is multiplied by 5. Alright, now the first thing we're going to do is actually run f. Now, we know that the IOC of base, of course, is from 1 to negative 1, and we're going to actually calculate very quickly the IOC for this new version. Now, we can ignore the 5 and simply work with the negative 1 over 2. Sorry, negative 2x. And this is the default IOC with our r in the center, and we're simply going to solve for x, and this is going to involve having a very loud noise play in my ear. What? Alright, never mind. We're going to divide each side by negative 2x. And then simplify, and of course flip the signs so that it becomes this, negative obviously. And in order to run the function, we're going to pick a number in this interval in convergence, so we're going to be picking 1 over 4. So we're going to be running the equation 5 divided by 1 plus 2x, and we're going to be running with the example number 1 over 4. So that's going to be 5 divided by 1 plus 2 times 1 divided by 4. And I'm simply going to just throw this into the calculator very quickly because I am tired and don't want to be doing this video right now. 1 plus 2 times 1 over 4. Done that again because I accidentally put it into a bracket instead of a parentheses because I am an idiot. And you will actually see that the final value of this number is 10 over 3. So that's what the function at 1 over 4 is equal to. Now we're going to do the Taylor polynomial of this. Now we're going to modify the Maclaurin series of base, which as we all should know is 1 plus x2 plus x3, and that's a c instead of an x, and plus x4 plus x5. So that's base, and we're going to modify it by putting in 2x for every x, because of course in our modified version of base, sorry, negative 2x for x. So negative 2x, negative 2x. Pardon the syntactical error from not putting negative 2x in a parentheses, but I'm going to be going through this because there's a 2-minute limit, a 5-minute limit on these screen recordings. And that's going to end up with 1 minus 2x plus 4x squared plus minus 8x cubed plus 16x fourth plus 32 x to the power of 5. Now we're actually going to get rid of the fifth term because in our Java series only runs up to the fourth term. So we're only going to do that just to keep up with it. Apologies, fifth term, but yeah. And of course, this whole thing is being multiplied by 5, as is the original. And now we're going to see what this equals. You can plug this into your calculator like I'm about to do to get the final answer. So I'm going to quickly plug this whole thing into my calculator and solve for it at 1/4. That way we can see what the doing the polynomial by hand, of course, equals. Plus 16x fourth. Okay, that seems about right. We're going to set 1/4 for x on my calculator and plug it into that equation, and we're going to see that this equals 55 divided by 16. Now 55 divided by 16 in decimal form is equal to 3.4375, and 10/3 up here is equal to, of course, 3.333. Now these are quite close, but of course these are quite close as this is an approximation, not an exact replica. But very quickly, we're now going to jump back into Java, actually, to modify the program to see how this runs. Okay, so here we are back in Java with the original base program. I went like Sean Connery for a second. So we're trying to modify this program so it'll run with 5/1 plus 2x. So we're going to have to modify this program. Now this part of the equation is already quite similar to ours because it's a plus instead of a minus. So what I'm actually going to do is remove all of these right here so we can just work here. Now to modify this for 5/2x, we're going to start off by multiplying it by 5, and to do that, the final result will actually be multiplied by 5, because of course that's the only difference between having 5 there or not having 5 there, a multiple of 5. But another thing we need to do is we actually need to multiply each of these x values by 2. So we're going to just put 2 here and multiply it by e, and we're going to put in its own parentheses just to be safe. And that should be all we need. So actually, let's see how it runs. We're going to run the program and watch the whole thing crash. All right, wait one moment. All right, we are back. I had removed the actual declarations of each function, so we're going to run. So I just put those back in, and we're going to run the program again. We see that it now says 5/1 plus 2x, and we're going to be putting in our original number, 1/4, to see that it crashes. All right, going to leave again for another moment. Resume. Right, of course, we can't put 1/4 because it needs a double, so we're going to put 0.25 because of course this program can't take 1/4 because it's dumb. And we see that the answer given here is 3.475. Sorry, 0.4375. So we're going to run back to our problem, and we're going to see that this is actually equal to our approximation using the Taylor series, since of course we use the Taylor series. If we had gone up to the 5th term, we'd get a slightly different, albeit more accurate answer. But of course that's how the Java program works, how we can modify it. Just to make sure that no one's confused, I'm going to actually go over my changes to the program again. I changed this println statement just so that it's a bit more accurate to what we're doing. I deleted the first part where it just did normal base because that was sort of pointless to us. For one thing, I multiplied e by 2 for the not negative 2 because it was originally negative e, in order to account for it being 2x, okay, instead of just normal x. So we need to multiply each value by 2, and I had the final result multiplied by 5 because, of course, it's 5 over 1 plus 2x. And, of course, I had to fix the program because I got rid of the initial declarations. And, of course, it gives us a Taylor series up to the fifth term. All right? So coming up now, I'm actually going to be assigning you the practice problems for you to run by hand or by Java, depending on what the teacher actually wants you to do. So I'll see you there. Alright, now we are going to be walking through the rest of the notes. Right, so what we're seeing right now is basically we've plotted the sine graph, obviously here, as you can recognize it, and we're slowly adding terms to the Taylor series for sine, and watching how it becomes more and more accurate over time. Alright, so for example, okay, in this first, we simply have sine of x and then just x. And we see that it is accurate right about here. Okay, but everywhere else it seems to diverge. But once you add the second term for the sines Maclaurin, suddenly it's more accurate. And in more terms, makes it more accurate, and more accurate, and more accurate. Okay, and this is showing that basically you can use these polynomials to approximate the function of a given value of an x within the interval of convergence. And sometimes the interval of convergence is all real numbers. Okay? And if we keep looking over here, we can see that it gets more accurate and more accurate and more accurate until at the very end here, once we're up to this term, over 17 factorial, which is a value used for the Taylor series effect, you can see it's almost completely accurate, only seemingly diverging right here. Of course, as you go farther out, it'll diverge more. So it asks the question now, what do you observe as terms are added to the polynomial in comparison to the sine function? Well, there's simply one determination that we can come to, is that as additional terms are added, the polynomial more closely matches the sine function. All right. So now we're going on to the next page. So this formula for the Taylor series. Apologies. Yeah, alright. So this is the basic idea of the Taylor equation. The function at a plus the derivative of the function at a times x minus a plus the second derivative of the function at a over 2 factorial times the factor times x minus a over 2 factorial, and on and on and on. And basically the generalizes it, the nth derivative of the function at a over n to the power n factorial all times x minus a to the power of n. Now, n at the very first term is 0, which is what, okay, so the 0th derivative, or the original function at a, over 0 factorial, which is 1, okay, times x minus a to 0, which is just 1, which is why the original term is just the original function at a. Now, don't worry. You do not need to know derivatives to do this. We'll be giving you all the derivatives so that you can understand it. All right? So we're going to be looking at cosine. All right? So our initial term, our a seems to be at a equals 0. That's what we've been given, a equals 0. So we're going to set 0 for each of these. Okay. Our original term is cosine, and I'm going to be giving you all the derivatives. The derivatives of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine, and the derivative of sine is cosine. So it returns back to the original function for trig, and we're going to be just solving all of these at 0. So of course cosine at 0 we should know is 1, negative sine at 0 is 0, cosine at 0 is 1, so negative 1, sine at 0 again 0, and cosine at 0 is 1. Right. So this is all the f of something. So the first derivative of a, second derivative of a, and fourth derivative of a. And since a is 0, all of these x minus a's simply become x's. So let's solve. That'll be 1 plus 0 times x minus, well, 0, plus negative 1 times x minus 0 squared. All right. Plus 0 times x minus 0. All of this was over the second factorial, over the third factorial, because again this is squared, and finally plus 1 times x minus 0 to the fourth over 4 factorial. Sorry that this goes out. Now this times 0 and this times 0, so it cancels out. So it finally becomes 1 plus negative x squared over 2 factorial plus x fourth over 4 factorial. And there we go. That's that is the Taylor series for cosine at that value. All right. Now this is asking for the key point, the Taylor series for sine and cosine. So I'm just going to simply throw that up. For cosine, we just figured it out. It's 1 minus x squared over 2 factorial plus x4 over 4 factorial. All right. So that the video cut up for a moment, but anyways, so the Taylor series for cosine is 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial dot dot dot, while sine is x minus x cubed over 3 factorial plus x5 over 5 factorial. Sorry for the mess, but it's basically just a pattern here. So now we're going to be looking at the example, creating more series using cosine, finding the series for 3 times cosine 2x at a equals 0. Now, basically, this works like how base was working before, where we simply submit where we simply insert the changes. So the difference between cosine x and 3 cosine 2x is that x has been replaced with 2x, and the whole thing's being multiplied by 3. So we're going to start with the Taylor series for cosine x. So that's going to be 1 minus x, not x3, sorry, x cubed over x2 over 2 factorial plus x4 over 4 factorial. All right. Now it's asking, look for the difference in the series x being multiplied by 2, -2x. Pardon, ignore these instructions. They're actually wrong. They seem to be for a different problem. But basically, we're just going to submit our changes. We're going to place all the x's with 2x, because 2x is what's different between them. So it's going to be 1 minus 2x2 over 2 factorial plus 2x4 over 4 factorial, and the whole thing's going to be multiplied by 3, right there. And if we simplify it, that's going to be 3 minus 2x plus 16 over 4 over 6, or 3 over 2x4. That should be right. Let me just quickly check. Of course, multiplying each of these by 3, which makes this 2 times 2 is 4. 2 times 2 is 4 over 2, making it 2, so that becomes 6. And 2 times 2 is 4 times 2 is 8 times 2 is 16 over 4. So that leaves it being 4 over 6 times 3, meaning that it's 2. So that leaves it just being 2x4. All right, and that's our value, 3 minus 6x plus 2x4. Now we're going to create the Taylor series for negative x. The video is about to run out of feed in a moment, so I'm just going to pause. All right, next part. Create the Taylor series for cosine negative x. All right, so we're going to be simply submitting negative x into the cosine, which Taylor series, which we still have here. So that's going to be 1 minus negative x squared over 2 factorial plus negative x fourth over 4 factorial, which do... that's another example, we'll get to that in a second. Which simply becomes 1 minus... yes, 1 minus x 2 over 2 factorial plus 4 factorial. It seems to just be the same exact answer because the negatives always simply cancel out because they're all in even under even powers. So yeah, alright, now we're going to be creating the Taylor series for 5 times cosine x plus 1. Alright, so this is a bit different. We're going to be replacing x with x plus 1. So, we don't actually have a lot of room here, so I'm going to just quickly do this. So basically we're just going to put in x. We're going to place all the x's with x plus 1, so that's going to be x plus 1 squared over 2 factorial minus and plus x plus 1 4 over 4 factorial, and the whole thing will be multiplied by 5. We could simplify that, but this is best. That would just become 5 minus 5 times that over that plus 5 times that over that. We understand these basic principles at this point. It's probably... let's move on to this. Okay, we're going to be working with sine now. So we're going to start off with the Taylor series for sine, which is just simply x minus x cubed over 3 factorial plus x5 over 5 factorial. And remember that these go on and on and on, but it's the first few terms we're going to be looking with. So what does it want us to do? We're only working with sine to the x squared, so we're just going to replace all the x's with x squared. So it's going to become x squared minus x squared to the third over 3 factorial plus x squared to the fifth over 5 factorial. And when we simplify as the instructions, it simply becomes x squared minus x6 over 3 factorial plus x10 over 5 factorial. So that's good. There's a few more practice problems. So sine 1 plus 2x times 4. So I'm just going to simply show you this. We already know what sine is, so that's going to be 1 plus 2x minus 1 plus 2x cubed over 3 factorial plus x 1 plus 2x 5 over 5 factorial, and simply multiply all of these by 4. The video is about to cut out in about 20 seconds. We can quickly rush through this one. So it's going to be 3x minus 3x cubed over 3 factorial plus 3x 5 over 5 factorial. Multiply all by -2. Video is about to cut out anyways. So alright, I'll pause and then we'll start again in a second. Alright, so now we have to multiply all this by -2, so it becomes -6x plus 2, 3 to the power of 3 is actually 27, so that'll be 54x3 to the third over 3 factorial plus 3 to the 5 is actually, let's see, 243 to the x fifth over 5 factorial, and simplifying it, 54 divided by 3 factorial is to 9, so this whole thing simply becomes negative 6x plus 9x3 plus 243 divided by 5 factorial equals 81 over 40x5, and that's our final right there. Alright, now it's the packet is making us quickly review what we've seen. We've seen base 1 over 1 minus x. We've seen a modification of base where x is replaced with negative x, or 1 over 1 plus x, and of course cosine and sine. We've seen all of that. We're going to quickly look at the general terms, just in case in case there's some confusion. The general terms are basically, it shows us every term of the Taylor series, no matter how high we want to go up. So obviously base is 1 plus x squared plus x3, meaning that its general is x to the n, where basically every term starting at 0, and then 0, then 1, 2, and 3, so that means that one. The Taylor series for the modification of base, where x is simply replaced with negative 1, we simply add negative 1 that's being multiplied by n, so that it goes back and forth. That's that one. Cosine, again, it alternates between negative and positive, so we have the negative 1 to the n, and then since it's every one of the x's are to an even power, including this one. This is just x to the 0. 1 is simply x to the 0. So basically it's x to the 2n, and of course over 2n factorial, because it's always even. This is over 0 factorial, which of course is simply 1. And sine is in reverse, but with odd, so it's the negative 1 to the n because it's alternating, and then it's x to 2n plus 1, so it's always odd, where the first one is 1, since this is x to the 1, over 2n plus 1 factorial. Alright, moving on, we see over here, alright, so right now we simply just have some base questions right now that I actually want you guys to go through it, but this is simply the answer piece. So pause. So do this work, and then unpause to see the answers, or if you're confused, watch so you can figure it out. So it's asking for basically the Taylor series for all of these functions, and all of these are simply altered versions of base. So this is 1 over 1 minus x3. Now, base, remember, is 1 over 1 minus x. So what's happened is simply that x has been replaced with x3. So we're going to take the Taylor series of base and simply replace all the x's with x3. So that would be 1 plus x3 plus x3, 2. And we're going to stop off the fourth term because it's asking for the fourth term. x3, 3. And that simply becomes, when you simplify it, 1 plus x3 plus x6 plus x9. The next one, this is another altered version of base, where all the x's are replaced with negative 2x. Because remember, base is 1 minus x, but this is 1 plus x squared. So we're going to replace all the x's with negative x2, and the whole thing's multiplied by 2. So that's going to become 1 minus x2 plus minus x2 squared plus minus x2 cubed, and the whole thing is multiplied by 2, and we're already running out of room, so I'm actually going to go to the bottom here, and just through some simple algebra we can see that this is going to be 2 plus 2 minus 2x2 minus 2x4. Apologies, not minus 2x4, because the negative is actually underneath an even one. So that's going to be plus 2x4 minus 2x6. So that's our answer for this one. Pardon the answer key, it's quite wrong. It said the answer key here seems to think that the 2 is going underneath the power. It is not, so ignore that. This is the actual answer. The next one, okay, so this is an altered version of base where simply the x is replaced with 4x, so that's going to be 1 plus 4x plus 4x cubed plus 4x, sorry, x squared plus 4x cubed, which simplifies to be, let's go in this direction actually, 1 plus 4x plus 16x squared plus 64x cubed. This next one is a bit more complicated. This is where x is being replaced with negative x over 2. So we're going to run through that. That's going to be 1 plus negative x over 2 plus negative x over 2 squared plus negative x over 2 cubed. And we're going to go down to the bottom again. So remember distributing your exponents correctly. This is going to be 1 minus x over 2 plus x squared over 4 minus x3 over 8. Alright, and that's of course the first 4 non-zero terms. The answer sheet that we've been given goes to 5 for some reason. That's alright. And the final one is actually very simple. It's simply base times 64. So it's going to be 1 plus x plus x2 plus x3, the first 4 non-zero terms, times 64, or 64 plus 64x plus 64x2 plus 64x3. Alright, and that's the final answer. Alright, so right now I'm actually going to jump into the program showing how sine and cosine with in Taylor series, the Java program, and after that you'll be assigned another function to work with. Alright, see you there. Alright, it's 3 a.m. Welcome back. We're going to go through this program. It's Java. You all know it. Here's a bunch of variables. They're going to store stuff. It's asking us to enter an x value. Oh, look at that. We've entered it. Now it's calculating the Taylor series for this type of sine. There's a 5x instead of just a 5. Look, you can see it's there. It multiplies our variable times 5 the entire time and puts it through the Taylor series for sine. Look, our variable to 3 over 3 factorial. These are the factorials. 3 factorial, 5 factorial, and 7 factorial, 9 factorial. We calculate it with sine. We find the error. We print them out. Same thing with cosine. Watch. 1. Okay. It finds that the value of 1 at sine 5x is negative 0.95. The Taylor series is 0.089. The difference is 0.104. Let's try that at cosine. It finds that at 2 cosine 3x, it's negative 1.97. Taylor series says it's negative 1.94. Pretty damn close approximation. There's the error. It's not a lot. I'm going to change this so that it's for cosine alone and not 2 cosine 3x. You know what that means? It means getting rid of the times 2 and the times 3. Because screw 'em. It's 3 a.m. I've recorded this about 4 times now. Run. 1. We don't care because that's sine. Ta-da! Cosine. Cosine x at 1 is 0.54 that. The Taylor series at 1 is 0.54 that. The error is so small we can't even represent it as a number without scientific notation. That's how damn close we are. There you go. That's how the program works. I know, look at that. It even says cosine now. The first time it said 2 cosine 3x. Done.
I'm waiting for you. I stood and watched as time divided in two. I'm standing in place, regret on my face, my broken heart.